Now let's move on to the relationship between displacement and strain. So let's first take a look at talk about how to describe motion. The geometry of a continuum body can be represented mathematically by embedding it in a Euclidean vector space R3, where every point in the body can be represented by a unique vector. So every point can be expressed by a vector. We denote the set of vectors corresponding to the material point as omega 0. And this embedding is called a configuration. And we are interested in comparing a deformed configuration with an undeformed configuration. So if we are looking at this figure, we can see that in the deformed configuration on the left and the undeformed one on the right. So we are comparing the right one with the left one. Then the deformed configuration can be assumed to be a function from f from omega 0 to omega. In the majority of continuum mechanics applications, there are a few restrictions. First, we assume that deformation between configurations preserves the distinction between material points, which restricts f to be bijective. It means all points in the undeformed space are also in the deformed space, and vice versa. Second, we assume that material points do not change their adjacent points. This restricts f to be continuous. In most applications, we add a third restriction of being smooth or differential on the possible choices for f. This ensures that straight lines on the reference configuration deform into smooth curves in the deformed configuration. And it also allows for the calculation of derivatives and the definition of a strain. The displacement function of a body is usually denoted by the function u from omega 0 to omega. Based on this definition, if we define the position of the material point as capital X in the undeformed configuration and X in the deformed configuration, then the displacement field is equal to X minus capital X. And Ux is a function of a capital X. So it has 3 components. For example, here we have a pure rotation Q. And so X can be expressed by Q and X. It's equal to Q times capital X. And then the displacement U is equal to X minus the corresponding points in the undeformed configuration, which is the capital X. So it's equal to Q minus the identity matrix times X. Now we will take a look at uniaxial strain measures. Assuming that the length of a bar is L0, and it is stretched to the length of L by exerting a force of F. Then if we define the ratio between L and L0 is as lambda. which is also called a stretch ratio. So there are three commonly used string measures that we can use to define how the length of the bar changes. The first one is engineering string. So engineering string is defined as the difference between L and L0 divided by L0. If we express this as using stretch ratio, it's equal to lambda minus 1. And the true string is defined as ln of L over L0. So ln is the natural log. So it's equal to natural log of lambda. And green string is defined as L squared minus L0 squared divided by 2 times L0 squared. So it's equal to 1 over 2 times lambda squared minus 1. So these strings have different applications. So if we plot these three strings together on a graph with respect to the stretch ratio, we can see that when the stretch ratio is around 1, they are quite similar. The difference is very small. But when it's beyond a limit, the difference is relatively large. And also we need to know that when given one stress, for example, if we know engineering stress, then we can find a stretch ratio. With knowing stretch ratio, we can also find true stress and green stress. So given one stress, we can calculate the other stress. When it comes to a small string tensor, this small string tensor epsilon is defined as the symmetrical part of a displacement gradient del u. And if we call u is the displacement function, del u is equal to this. So the first row is the partial u1 with respect to x1, x2, x3. And the second row is equal to partial u2 with respect to x1, x2, x3. And the third row is equal to partial u3 with respect to x1, x2, and x3. And then our small string tensor is defined by del u plus del u transpose divided by 2. And the component form of epsilon ig is equal to 1 over 2 times partial ui over partial xg plus partial ug over partial xi. So from this, we know that string matrix is symmetric. Because if we change ig, the epsilon ig is the same, is equal to epsilon gi. Now let's take a look at an example. If we have small x, if we know the relationship between small x and capital X, then we know that u is equal to small x minus capital X is equal to 0.2, 0.2, 0.2, 0.2, 0.3, 0.1, 0.9, 0.5, and 0. And then del u is equal to this matrix. So the small string tensor is equal to 1/2 times the del u. This is the del u. Sorry. This is del u. Is equal to 1/2 times the del u plus the del u transpose. So it's equal to this matrix. So in the case of small deformations, the small string tensor can also be used to calculate engineering longitudinal and shear strings. Let's take a look at an example of a normal string. So if we have a very small length, dx1, and the displacement function of this piece is u1, then after deformation, the left side have a new position, which is x1 plus u1. So the right side will have a new position, which can be expressed as x1 plus u1 plus dx1 plus partial u1 over partial x1 times dx1. And then the new length of this unit is equal to this part minus this part. So the new length is equal to dx1 plus partial u1 with respect to x1 times dx1. And the original length is dx1. Then we can find the epsilon 1,1, which is equal to L minus L0 divided L0. So which is equal to partial u1 with respect to x1. And this is equal to the small string tensor. It's epsilon 1,1. So now let's take a look at engineering shear string. Based on the definition of a shear string, it's equal to the change of the angle. So engineering shear string is equal to, for this situation, is equal to theta 1 plus theta 2. So if we have a square with the length dx1 and dx2, then after deformation, it will look like this. So after deformation, the left bottom color will have a new coordinate. So along x-axis, it's x1 plus u1. Along y-axis, it's x2 plus u2. So this is x, this is y. So now if we take a look at left top point, so we can express its displacement around x-axis as this: x1 plus u1 plus partial u1 over partial x2 times the length dx2. And if we take a look at the red bottom color, then our new coordinate along y-axis is equal to x2 plus u2 plus the partial u2 over partial x1 times the length of the element, which is dx1. Then if we calculate this small piece with respect to this, is equal to sigma 2. And this divided by the length of the element is sigma 1. So when we plug in, sigma 1 is equal to this component, and sigma 2 is equal to this component. So after this, we can find the engineering shear string is the partial U2 over partial X1 plus the partial U1 over partial X2. So when we compare this to the small strain tensor, we get engineering shear strain is equal to 2 times shear strain tensor from small strain theory. So small strain tensor have a disadvantage, which is it can't be used to measure pure rotation. For example, here we rotate this red triangle to a new position, and it the new position is here. Then we can follow we can calculate the relationship between x and the capital X, and then we can find displacement function u is equal to q minus identity matrix times capital X, and del u is the derivative of u with respect to x1, x2, x3. Then we get rid of this, and del u is equal to this. And then we can plug in del u, because based on small string theories, epsilon is equal to del u transpose plus del u divided by 2. And after simplification, we get a matrix like this. So sigma 1, 1 is equal to cosine theta minus 1, and sigma 2, 2 is equal to cosine theta minus 1. This is not equal to 0. But since we are doing a pure rotation, this geometries were not stretched or compressed. So the string should be 0. So that's why we can't use the small string theories for pure rotation, especially when this angle is very large. So when the theta is close to 0, cosine theta is equal to 1. So this is acceptable. But when theta is close to 90 degrees, so this will give us 1. So this is not acceptable. It's a judgment call. So, but you need to be aware of this limitation of the small string tensor. Now, let's take a look at another stress tensor that does not have the disadvantage of a small string tensor. Green string tensor. It is defined as 1/2 times F transpose times F minus identity matrix. So F is the deformation gradient. So if we know the relationship X is equal to QX or any other relationship, we just need to know this matrix. And this matrix is F. Then we can calculate del u. Del u is equal to F minus identity matrix. And then we plug in, then we can rearrange this F is equal to del u plus identity matrix. Then we plug in this into the above formula. We will get some. We will get something like this. And if we compare green string tensors with small string tensors, we know that we have a third component for green string tensors, which is equal to del U transpose times del U divided by 2. We compare it to when we compare it to this. So we will have a third component, green string to small string tensor. Yeah. So because this is equal to this. So let's test this with the same example. So when we know we have a pure rotation here, and the relationship between x and capital X is x is equal to q times the capital X. So f is equal to q, and then we plug in f, we can find the green string is equal to 0. So the green string doesn't have the limitation that a small string has.